Right, let's push on then. What I want to have a look at today is radioactive decay, and there's a number of words in that sentence that need explaining, so let's just remind ourselves. Some nuclei are quite grumpy, okay? Some nuclei have the wrong number of neutrons and protons, okay? We looked at an example the other day, which was carbon-12, which contains 6 protons and 6 neutrons. Very, very happy, incredibly stable, so stable it's the basis of your biochemistry and the cells that make life on Earth and stuff like that, okay? Put 2 extra neutrons in, so you've got carbon-14, 6 protons and 8 neutrons, and for some reason you get something that's really unhappy, all right? It's really grumpy, it doesn't want to go together at all, okay? Quite why that is, we don't fully understand actually. It's an interesting piece of physics. Why is the 14 and the 6, why is the 8 and the 6 wrong and the 6 and the 6 is fine? Again, that's something we're still scratching our heads over to a certain extent. Okay. The upshot is though, the way that it tries to become more stable is by chucking out mass and or energy. Okay. And this is called being radioactive. So I would actually, in your margin, perhaps draw a little grumpy face next to radioactive. That's what it means. It means nuclei which just aren't happy with their number of neutrons and protons. Okay? You just need to know some are and some aren't. And the ones that aren't are referred to as radioactive. Absolutely nothing to do with radio. All right? Couldn't be more distant. 2 bits of physics that have nothing to do with each other are what we're going to do today, and radio waves. Okay? It's an accident of history. They were both discovered about the same sort of time. And as people didn't know what was going on with this radioactive decay, they thought it might be linked to the other big mystery of the time, which was radio waves, and it wasn't, but the name has kind of stuck. Okay? The radioactive means unstable, it means grumpy, it means a nucleus that can't settle down, and is going to chuck out some mass or some energy. Okay? There are 3 ways in which it can do this, and they are called alpha, beta, and gamma. Okay? The 3 ways in which grumpy nuclei, or unstable nuclei, try and become more stable, they can throw out an alpha particle, they can throw out a beta particle, or they can throw out a gamma ray. Okay? And what we're going to do this morning is just have a look at the effect that that has on the nucleus that's left behind. Okay? So let's just do them one at a time. Alpha, you would be expected to recognise the Greek letter there, alpha. Okay? An alpha particle turns out to be made up like this. You might think, well, if I'm carbon-14, I'll just lose the 2 neutrons. And then I'll be carbon-12, and that's the end of it. It turns out it's more complicated than that. You can't do that for all kind of clever quantum physics reasons. That's not really very likely to happen. Much more likely is you'll either chuck out an alpha, a beta, or a gamma. So you are limited. This is why some things stay radioactive for long times, is because they're limited in the ways in which they can chuck out mass and energy. There are only 3, basically 3 permitted ways of doing it. Okay? The alpha particle, make a note of this, is made up of 2 protons and 2 neutrons. Okay? Let's take an example of a grumpy nucleus. And again, can I remind you about this way of writing nuclei? Chemical symbol, which they will give you in the exam. It's not a chemistry exam, you don't need to know those. 6 is the number of protons, it's called the atomic number. 14 is the number of protons and neutrons together, and that's called the mass number. Okay? Get used to seeing it written that way. I checked the other week, if you go into your chemistry labs, they've got periodic tables, and the little squares on the periodic table have these numbers the other way round. Okay? So I'm sorry, this is a different way of doing it to chemistry by and large. Okay? Now, 14,6 carbon is going to decay by alpha emission. Okay? I'm pretty confident that doesn't actually happen. All right? If you look up carbon-14 on the internet, you can find out which one does it do. I'm fairly confident it doesn't do alpha, but it's just an example that we can use. Okay? Now, what are we going to have left over? Well, think about it. What are going to be the atomic and the mass numbers of what's left over? Imagine you are 14,6 carbon. That's 6 protons and 8 neutrons. Visualise them in your mind. You're going to chuck out 2 protons, 2 neutrons. Can someone do the maths for us? What are we going to be left with? What will the nucleus look like after it's chucked out 2 protons and 2 neutrons? If you started off as 14 and 6. That's it. You're going to have, well, you're going to have 4 protons. Oh, sorry. You're going to have 4 protons. Are we all happy with that? Carbon has 6, okay, and alpha emission you lose 2. Pretty obviously, you're going to have 4, okay. What's the new mass number going to be though?
10.
It's going to be 10, isn't it? All right, because remember the top number is not the number of neutrons, it's the number of neutrons and protons added together. A nice way of thinking about it, I always say, is to imagine that there's no, it's like colourblind. If these are red and black snooker balls, for mass number, you just forget about the colours. You just count the fact there are 4 objects. The fact that 2 are protons, 2 are neutrons, doesn't make any difference. If you lost 3 protons, 1 neutron, still be the same thing. You've lost 4 things, okay? So we've been down to 10 and 4. If you have your periodic table handy, that would be quite useful. Hydrogen, helium, lithium, beryllium. Okay, number 4 on the periodic table, you can check it for me, is beryllium. Okay, and so you go from a nucleus of carbon to a nucleus of beryllium. You can see already, gentlemen, this is not a chemical equation. If you write that sort of thing in your chemistry book, that's going to go badly. All right, what can you make from carbon and oxygen in chemistry? You can make carbon dioxide or something like that, just rearranging the carbon and the oxygen. Okay, here we're turning carbon into beryllium, all right? That's just not right. As I said, this is a nuclear equation. Let's make a note of that. What we're doing here is we're writing a nuclear equation. Now, in nuclear equations, it basically means you can change elements, which I'm sure your chemistry teacher told you right from the word go is not allowed, okay? H2 plus O makes H2O. It doesn't make gold, all right? We'll turn lead into gold a bit later on, as that's something we can do in physics. All right. Now, this equation ought to balance, because what else has come out? We haven't turned 14 into 10. We've just turned 14 into 10, and 4 of them have left the building. All right. So we need to write in the alpha particle as well. Okay. What would be the mass number of an alpha particle? It's got to be 4, isn't it? All right. So the mass number of an alpha particle would be 4. Okay. The atomic number, well, if you look at the number of protons, pretty obviously the atomic number is 2. Can I recommend that you learn that bit? Because that will be true for every single alpha particle. If you get a question in your exam that's to do with alpha decay, that's it, all right? 4 for the mass number, 2 for the atomic number. Why? Because it's 2 protons and a total of 4 particles. Can you see, I mean, I'm sure you've done balancing equations in chemistry. Can you see this one balances 2? Look at the top line. 14 is broken into 10 and 4. That's okay. So tick there. And 6 has broken into 4 and 2. Again, that's fine. So this is how nuclear equations work. The rules are different to chemical equations. You can change elements if you want to, but you must make sure your mass numbers add up along the top line, and you must make sure your atomic numbers add up along the bottom line. Okay? Just a bit of notation. I don't quite know why, but this is the way it's done. You need to know these words because they get used in the exam. The particle that you started with is called, the nucleus that you started with is called the parent. You'll see that word used in the exam. They'll say a parent nucleus or something like that. And the product, the nucleus that's left there after the alpha particle's gone, is called the daughter. Okay? It's quite possible that the daughter particle might be radioactive. In fact, we can work this out if you've got your periodic table in front of you. Can you tell me what's the mass number on the periodic table for beryllium? What's the bigger of the 2 numbers provided for beryllium? 9. So the stable version of beryllium, perhaps don't put this in because it might confuse you. If you look in a chemical periodic table, they're obviously interested in the ones that actually exist, the ones that actually stay around on the bench long enough for you to do an experiment. So if you look at a chemical periodic table, for beryllium, it's got it as number 4 on the periodic table, position number 4, and it gives a mass number of 9. That means that beryllium 9 is the most stable version, all right? Beryllium 10, therefore, we'd have to look it up in more detail. Pretty obviously, beryllium 10 is not the normal version of beryllium. What word should I be using instead of version? Isotope. And if you don't use that word in the exam, you are going to lose marks, all right? So this is the stable isotope of beryllium according to your periodic table. What we've made here, beryllium-10, is probably not going to be stable. That's going to decay further, and surprise, surprise, that would be called the granddaughter. Okay? And if the granddaughter was unstable, then what you're developing here, a term we'll come back to a bit later, is a radioactive decay series. Okay? The nuclear waste from nuclear power stations, the uranium and stuff, will eventually turn itself into lead by radioactive decay, but it takes about 10 or 12 steps. It goes through a whole series, okay, of decays before it gets there. All right? To be honest, in the GCSE, you tend to have single ones. You would just have something, parent, decaying into something, daughter, by alpha, beta or gamma. Okay? But in reality, many things have whole series of decays. Okay? Right, can we just then do a little summary thing for alpha? What could we say to summarise the effect of an alpha particle on your mass number? What effect does alpha decay have on your mass number? Anyone? So again, this will be the same for any alpha particle. So can you perhaps make this really clear in your notes? Okay. Alpha decay is going to be -4. Anytime there's alpha decay, you lose 4 from your mass number. And pretty obviously, you lose 2 from your atomic number. Okay? And this is a mad example I've made up for today, but these numbers here will be the same for any. All right? And these are clearly numbers that you need to bring to the exam. An alpha particle is 4 on the mass, 2 on the atomic, and therefore losing it means you lose 4 off the mass number, 2 off the atomic number. Okay? Is everybody happy with alpha decay because it's the easier of the two? Okay? The trickier one is beta decay, and for that reason I think it's slightly more often examined. Beta takes a bit more thinking about, as we'll see in a moment. Okay? Anything with that? I'm going to rub that off now. Okay? Right, let's have a look at beta decay then, and let's see if we can do the same job. Okay? Let's have a look at beta decay. Greek letter beta. You'll sometimes see it written as beta minus decay. There are two kinds of beta decay. The one we're doing is the more usual one, which is called beta minus. There is a beta plus decay, which you don't need to know about. Okay? Now, beta minus decay is rather strange because it involves the nucleus giving out a fast-moving electron. Okay? Can anyone see a problem with that? What's the difficulty with a beta particle coming out? It was discovered some years after it was called beta particles that they're electrons. Beta decay is very strange because it involves giving out of an electron and there aren't any electrons. It's like taking a rabbit out of a hat when there weren't any rabbits in there. Okay? How on earth can it give out an electron when there aren't any electrons? The electrons live around the outside of the nucleus, and in the centre you've got the proton and the neutron. Okay, let's have a look then at how we solve this mystery. And for this, let's go back to 14,6 carbon. All right. What I'm going to ask you to do is a bit of a chore, I'm afraid. What I'm going to ask you to do is to actually draw them. So can you just draw yourself 6 protons and 8 neutrons? We actually need to draw the nucleus. I'm sorry there's so many of them, but you've got here 6 protons. They don't need to be half and half like me. You can jumble them up how you like. Can you just draw yourself a carbon-14 nucleus? Let's go back to our 14,6 carbon, and let's imagine that it gives out beta minus, that it's a beta emitter. Okay? Draw the nucleus, because as I said, beta is the tricky one. This is the one you've got to get your head around. Alpha is taken off 4, taken off 2. Certainly for the harder exam questions, they tend to go for this one. So it's important that you understand what's going on. All right? Alpha particles largely obvious, alpha emission rather. Beta emission is more tricky. Okay, so let's get our heads around it. Can you draw yourself a nucleus, put in 6 protons, 6 filled in dots, and 8 neutrons, empty dots. Okay? Now, we're going to give out something. We're going to give out a beta particle. Okay? And we're going to have something left over. We're going to go from a parent nucleus to a daughter. All right? And we're going to use that to write down the equation. Now, the big mystery then is how the electron can come out. Okay? because as you can see, the nucleus contains 6 protons and 8 neutrons. What has to happen beforehand, a good way to think about this, is there's a reaction goes on inside the nucleus before the beta decay happens. With our Geiger counter, all we see is the electron coming out, but that's a sign that something has gone on inside the nucleus to allow that to happen. So if you like, what's the step before beta decay can happen? And it involves one of the neutrons. Okay, so focus in on your diagram on one of your neutrons. Okay, and what happens is one of the neutrons basically turns into a proton. Now you might think that sounds a bit much, just one particle turning into, like saying a table can turn into a chair. That sort of thing doesn't happen, and this is where nuclear physics, you've kind of got to, requires a lot of imagination. You've kind of got to think in a different way to the world around you. If I said this textbook turns into that textbook by magic, you'd go, no it doesn't, that never happens unless you've like cheated or something. That rule of, I don't know what you'd call it, common sense, persistence of objects or whatever you might want to call it, objects generally stay as they are. That mug has been there for some time now and it's staying as a mug. It hasn't made a change into a gold block or something like that. I've been watching it closely. It hasn't turned into anything. Okay? That's a fundamental rule of common sense in what we call the macroscopic world, the world of real big objects that contain squillions of atoms. Okay? Key thing you need to get your head around today is in the world of single particles, what we call particle physics, being a particular particle isn't quite as cut and dried. A neutron turning into a proton is no problem at all. Particles turning into each other, 2 particles turning into nothing, turning into 2 particles, those things happen all the time. Okay? And there are some rules. You might think, well, this is just mad, you can just change things around how you like. No, there are some definite rules that still apply, some of them quite familiar ones, like conservation of energy. But the rule of staying the same particle doesn't happen. In particle physics, in big reactors, all sorts of things like that, and experiments, constantly seeing one particle turning into another happens all the time. Okay? So neutron turning into a proton, you might put your hand up and say that defies common sense. Yes, it does, because common sense doesn't apply here. But there are some rules of physics that do apply, which will mean that that can't be complete. A neutron can't turn into a proton on its own, because I'd be breaking a really important law of physics. Think what you know about a neutron and a proton. And there's something there that doesn't balance yet. I haven't finished the equation. Yet, there's something that doesn't balance. That's it. If we look at the charge, it's 0 for the neutron and +1 for the proton. Now, there is a law of physics called conservation of charge. Your chemistry teacher probably doesn't mention it to you, although it is the absolute foundation of their entire subject. If an atom loses 2 electrons, it becomes a +2. Have you done that kind of thing? Well, what are you keeping account of there? What are you checking there? What are you conserving there? You're conserving charge. An atom can't lose 2 electrons and stay neutral, can it? It has to become +2. The +2 and the -2 add up to the 0. So, although you may not have noticed it, charge, you are not allowed, you are absolutely not allowed to change the amount of charge. So if we're going to turn a neutron into a proton, we would have to turn it into something else as well, which had a negative charge. Okay? And think about the masses. A neutron is only a little bit bigger than a proton, so this particle here would have to be very, very tiny. You couldn't turn it into like a negative proton, because then you've got 2 lots of mass when you only put 1 in. Another law of physics, conservation of mass. Okay? There are rules about what you can do, common sense not being one of them. To conserve charge, this particle must be negative and very small to conserve mass. And it is, in fact, the electron. Okay? The neutron turns into a proton and an electron. And you might think that sounds a bit much. What do you know about a neutron? It's got a mass of about 1 and a charge of 0. Well, compare a neutron, gentlemen, with a proton with an electron glued on. How much mass has that got? About 1. How much charge has it got? 0. It's a neutron. For complicated quantum physics reasons we won't go into, every now and then, a neutron decides it wants to be a proton and an electron. Okay? You might think, I don't like the sound of this, but I am conserving charge, I am conserving mass, although it's beyond the A-letter GCSE, I am conserving energy as well. All right? I haven't broken any of the important laws of physics, and common sense is not one of the important laws of physics. Okay? Is everybody happy with that? Are electrons allowed in the nucleus? No. So the electron leaves. And that, you can draw a little eye or something. Obviously you don't stick your eye in nuclear experiments. This would be like a Geiger counter or something. But this is what we see. So the electron then goes zooming out. All right? And that's the thing we detect as... It was called a beta particle originally because when it was first discovered, the electron hadn't been discovered. They just called them beta particles, but they are actually electrons. Okay? Now, very importantly, can you go back to your diagram? Can you see? The neutron that you decided to turn into a proton, can you now go back and colour it in as a proton? Very importantly, one of your neutrons has become a proton. All right, go back to your diagram and change that. You've now got, I think you can see, very importantly, you've now got 7 protons. All right, you did have 6, but for beta decay to happen, it requires one of the neutrons to turn into a proton. Okay? So let's have a look at what we've got now. Have we still got 14 particles? We have. It's a nice way to think about it. It's a rearrangement. Beta decay is a rearrangement of the nucleus. Have we actually lost any of the nuclear particles? We haven't. We've still got, so let's fill in the daughter, we've still got 14. All right? Have we still got 6 protons? No, we haven't. We've now got 7. Okay? We've now got 7 protons out of a total of 14. Why have we got 1 less neutron? Why have we got 1 more proton? Because beta decay involves a neutron turning into a proton. What's left? The nucleus is an electron whose mass we ignore. It's really, really tiny, tiny fraction, a couple of thousandths of the mass of a proton or a neutron. Okay? If you check the periodic table, I think I'm right in saying nitrogen. So you've now got the daughter product here. The daughter is 14,7 nitrogen. Okay? The beta particle is going to be a bit tricky to fit in. What would be a sensible number to put in for the mass number?
0.
It'd be 0, wouldn't it? Now, the electron does have a mass, but it's incredibly small, even compared to a tiny proton. And so for our purposes, we can just call it 0. And then look, 14, 14, 0, you see? Just like we did with alpha particles, the idea, the top line balances. 14 goes to 14 plus 0. Okay? Now, this is where it's a bit weird on the bottom. There's a number of ways of looking at this. If I say to you, what's the atomic number of an electron? How many protons are there in an electron? That's just a stupid question. There's a mathematical way of doing it. Maths people, 6 goes to 7 and minus 1. And again, although this is rather weird, can you make sure in your notes you've got that really clearly? Because this is the bit you need to bring to the exam. If they say complete this nuclear equation for beta decay, you've got to know that the mass number of a beta particle is 0 and the atomic number is minus 1. An electron contains minus 1 protons. Again, that's not really helping. I think you can see it's got to be like that to balance. If 6 is going to 7, then that has to be minus 1. Can I just show you quickly a way of understanding this minus 1? Let's go back to 14,6 carbon, which we've rubbed out now. Go back to your original 14,6 carbon. This 6 is here because it's the number of protons. It's the definition of atomic number. But if I said to you 14,6 carbon, how much charge is there on that nucleus? Think of 14,6 carbon. How many units of charge have you got on that nucleus? 6, isn't it? When you count the protons, what are you also counting? You're counting the charge, aren't you? So if you like, if you're bothered about this, you can think of the atomic number. Don't write this in the exam, just use it in your mind. You can think of the atomic number like the charge number, okay? Because when you count the protons, you are counting the positive charge, all right? Let's ask the question the other way then. What would it be sensible to have as the charge number for an electron? Can you see? Minus 1, all right? Either way round, you've just got to learn that. You must know alpha, 4, 2. Beta, very strange, 0, minus 1. Okay. Let's just finish it off then, like we did last time, with the effect of beta. So the effect of beta on the... what's the effect of beta on your mass number? Nothing. Okay. What's the effect of beta decay on your atomic number? This is the trickier one. What's the effect of beta decay on your atomic number? What's our atomic number done? It's gone up, hasn't it? Okay. And this is the bit people find really, really spooky. Because decay sounds like losing something, and you do. An electron goes out of the nucleus, and your atomic number goes up. All right? Alpha decay, you lose 2 protons, your atomic number goes down by 2. Not too hard. Beta is very strange. All right? This is, again, you've got to bring this to the exam. All right? Beta decay, you are increasing the atomic number. Okay? So beta decay, you can see why. If you were the chief examiner, you'd do the same. Beta decay is the more commonly examined one because it's the harder one. You need to know a beta particle is 0 minus 1, and that means if you lose it, you all know from your maths about taking away negative numbers, if you lose a beta particle, no effect on the mass, and an increase in the atomic number. Okay? Anyone not happy with beta decay? Let's have a quick look at gamma decay, and the really good news is that there's almost nothing to do. Okay? Emitting gamma particles couldn't be easier. Okay? So let's have a look at gamma decay. All right. Again, let's, for the sake of argument, put this down. Let's have a 14-6 carbon. It's emitting gamma, and very simply, what's it going to do? Well, it's almost too easy for words. Stay the same. All right? A gamma particle is, as you know, not a particle really. You know from your electromagnetic spectrum from year 10, gamma rays, X-rays, ultraviolet light, infrared, radio. Gamma is just very, very short wavelength electromagnetic waves. So if you flick back to your year 10 exercise book and that big electromagnetic spectrum that we drew, then gamma rays are just the very shortest ones. Okay? And for that reason, think about it, bit of revision here. Because they're waves, how much mass have they got? 0. How many protons are they carrying with them? 0. What's the only thing they carry? Energy. All right? Let me remind you that waves carry energy, but they don't carry any mass or matter. All right? We said at the start, if you're radioactive, one way to get more stable is to check out matter. Well, there's alpha and beta for you. Or energy. Well, this is gamma. Gamma just chucks out energy. It's a way of radiating off some energy to try and become more stable. But it doesn't involve any change to the mass number. It doesn't involve any change to the atomic number. Okay? And so, it doesn't look like it, but the 14-6 carbon is now slightly more stable than it was. Not because it's lost particles, but because it's lost some energy. All right? A really silly way of thinking about it, which is wrong, but it's a good way of thinking about it. Think of the nucleus being too hot. How could it get less hot? It could just send out some infrared, some heat radiation. That's kind of what's happening here. It's just radiating off energy as gamma rays. Okay? You're not likely to get a nuclear equation problem for gamma because there's nothing happening. Okay? In particle terms, in periodic table terms, it has no effect at all. Okay? And that would be gamma. All right?